Okay, so this is your last video as a prep for the chapter 5 information. And what this is about is indeterminate forms of limits. And if you guys recall, when we were doing limits of functions, if we got a 0 over 0 or infinity over infinity, then that was an indeterminate form. And we had to kind of stop there. The only other thing we could really do was look for something that would cancel out, look for asymptotes, that kind of thing. So for example, if I take the limit as x approaches 2 of 4 times x squared minus 4 over x minus 2, and I plug that 2 in, then what I'm going to get is 0 over 0. Now the other option that I've got is to take that, factor the top part, because this x squared minus 4 is the difference of two squares. Now the x minus 2 will cancel. All right, remember wholes cancel out. So that cancels out. Then I can put the 2 in. 2 plus 2 is 4. 4 times 4 is 16, and that gives me my answer. And that's awesome, but sometimes we don't get that option. It doesn't work out quite that way. Let's take a look at another example. So right here, if we were to take the limit as x approaches 0 of the sine of x over x, what we would get is, we would get basically 0 over 0, because the sine of 0 is 0, and if we plug in 0 for x, we get 0, so that is indeterminate form. Now we've got an identity that already tells us this, but where does that come from? Now you're going to get to see where it comes from. Okay, so revisit. So what's going to allow us to work these forms is something called L'Hopital's rule, and you're going to hear it pronounced differently in different ways, but basically it's a French name. This was a French mathematician who devised this method. His name was L'Hopital. That's my French accent. I hope you like that. And so basically it's pretty simple, really. It's a simple concept, is that the limit as x approaches a of the quotient of two functions is going to be the same thing as the quotient of their derivatives. And this works. It gives you what you need, and it makes these limits of indeterminate forms really, really nice to work. But that means it has to be in indeterminate form. So you need 0 over 0 or infinity over infinity. So let's take a look at some other examples. So let's see how this works by using the examples we already have. Then we'll take a look at a couple more. So if we started out with our initial expression as x approaches 2, this idea tells us that if I take the derivative of this top part of the fraction of the numerator, I'm going to get 2x. The negative 4 is going to drop. I've still got the 4 because that's a coefficient. Okay. And then in the denominator, the negative 2 is going to drop. I'm going to be left with 1 with that derivation. Now if I plug the 2 in, 2 times 2 is 4. 4 times 4 is 16. You see I get the same answer that I did earlier by doing the canceling out of common terms. Now take a look at this one. So this is the one we were talking about before. We had to just memorize this as an identity, but now you can see the proof of it. So if I derive the sine of x, then I get cosine of x. The derivative of x is 1. Now if I take 0 and put it in for x, the cosine of 0 is 1. In other words, at 0 degrees, cosine is equal to 1 over 1, which is 1. Bingo! So this is like a Harry Potter spell. You see these that are in indeterminate forms, you can just go, L'Hopital's, bing! Or make whatever sound effect you want. It doesn't matter. All right. So this also then works for x approaching a from the left or the right, or x approaching infinity from the left or the right. Okay. Positive or negative infinity, I should say, not left or the right. I'm looking at the wrong sides here. So if you've got a constant value, or if you're approaching infinity for the positive or the negative, it doesn't matter. It's going to work. Okay. So again, though, you have to have 0 over 0 or infinity over infinity. Make sure you check for that indeterminate form first. Here's why. If I were to have started this out with the cosine of x over x and the limit as x approaches 0, then when I put 0 in for x, I get 1 over 0, which is positive infinity. Now, if I were to do L'Hopital's on this, I get negative sine of x over 1, put 0 in for x, this time I get 0. So infinity and 0 are not the same thing. You guys know that. This is why this will not work unless it is in indeterminate form. So you got to make sure you do that. Okay, so let's do another example here. What about cases like this? So if you've got this situation where you've got infinity minus infinity or 0 minus 0, you can use algebraic manipulation to get it into this form of 0 over 0 or infinity over infinity. And it's not overly complicated to do that. You just have to recognize possibilities. Okay, so think outside the box a little bit. So here I've got the limit as x approaches 0 from the right of 1 over x minus 1 over 1 minus cosine x. Now if I were to plug this in just to verify what I've got here, I end up with infinity minus infinity. Well, that's not what I need, but I can work with it. Here's how. I've got fractions. If I change these and combine them into one fraction with common denominators, in other words, multiply 1 times 1 minus cosine x, multiply this one by the x, I'm going to get this 1 minus cosine of x minus x over x times the quantity 1 minus cosine x. Okay. Now when I plug the 0 in for x, I get 1 minus cosine of 0, which is 1. So I get 0 on the top. Down here on the bottom, 1 minus 1, I get 0 on the bottom. Cha-ching. I got it. That's what I need. So now what that means is I can now do L'Hopital's rule. So from here, then, I can just use this, which is going to be simpler than this anyway, to find the derivatives. So derivative of 1 drops out. Minus cosine x is going to be sine x. Minus x is going to be minus 1. And then here, you could do that one of two different ways. You could multiply that through or whatever you want. But here is my derivative there. Now I can place that 0 in for my terms. I simplified this a little bit here. And then you've got 0 minus 1, which is a negative 1. 1 plus 1, or 0 minus 1, which is 0, which is negative infinity. It is an answer, maybe not a pretty one, but it is an answer that we can use. Okay, so let's take a look at one more situation. Just to reiterate what you've got. Let's do a simpler one to end on a good note. Let's do this one right here. So I've got the limit as x approaches 0 of e to the x minus 1 over 2x. If I were to substitute 0 in for x, I would get 0 over 0. That's the form I need to do L'Hopital's. So if I derive e to the x minus 1, and if I derive 2x, then I'm going to end up with e to the x over 2. Now if I put the 0 in for the x, e to the 0 is 1. 1 over 2 is my answer. So again, L'Hopital's rule requires us to place or manipulate a function into the forms of 0 over 0 or infinity over infinity so that we can derive and then find the limit of the derivatives. So I hope you find that helpful. It's kind of short, but there are plenty of examples in your book to go along with this. It's a nice concept. It's a pretty basic one, really, if you just know what it means.